didn't get it.
Roots. So we talked about square roots on Monday, right? Yeah. All right, kind of talked. We did a little example, and we mentioned if you had like x squared equals 25, we know the solutions are 5 and negative 5. So on the complex plane, there would be 5 plus 0i or negative 5 plus 0i. They're pi apart. Any other solutions, square roots in the complex plane, will always be pi apart. Now what's going to happen is, if it asks us for all cube roots, really the equation that is being set up is z cubed equals a dot. And in the complex plane, a cubic will always have 3 solutions. So if we just put this into some general form before we attack this one, if I have z to the n equals r cis theta, or a plus bi, what's going to happen is we'll have n roots. And they're going to be equally spaced apart. So if they're going to be equally spaced apart, think about the cube roots. How far apart will my 3 solutions be in terms of angles? I think so. Think of, if you've got the full circle, 120 degrees, right? Or since we're, so it'll always be 120 degrees. Actually, 120 degrees would be over here. So this would be 360 over n, or 2 pi over n apart. Because they have to be equally spaced out in order for this to work. So on this one, the cube roots will be 2 pi over 3 apart, or 120 degrees. So this is the generalization that we're going to need today. This is really the only layer that we're adding. The last new material that we're going to add to this chapter, which is the last new material for trig, which means we're done after, well, not really done. Keep learning, but we're done with trig after this right here, which is kind of cool. All right, so I don't want to be working in Cartesian here. Much easier to be working in polar, so let's start by converting. Zero plus 8i, we know we'll have a radius of 8. What would my argument be for 8i? Pi over 2. There you go. All right. And then we just apply Demoivre's theorem for our first answer. Take the cube root, and you can see that the radius is going to be 2. What's the argument going to be?
Pi over 6.
Pi over 6. Now with this, like you said, it's cube roots. We're going to have 3 unique solutions. The first one is 2 cis pi over 6. The second one is going to be 2 cis something. We'll come up with that. And then the third one would be, figure that out as well. So what we just need to do now is add 2 pi over 3 to each of these. Bless you. So if I add 2 pi over 3 to this, Elizabeth, what would you get for the first one? Okay. Did you get the second one? Or the third one? Or what do you want?
The last one.
The last one. Did you get that one too?
3 pi
and 9 pi over 6, and that last one reduces as Elizabeth said. These are the three answers in polar form. The question asks for the three answers in Cartesian form, so the last layer we need to do is just convert. What? What's cosine of pi over 6?
1/2. No, root 3 over 2.
Good one, good one. I like what you did there. All right.
747.
So cosine pi over 6 is root 3 over 2. So multiplied by 2, that would be root 3 plus sine of pi over 6, 1/2 over 2 plus I. So the first solution would be root 3 plus I. 5 pi over 6, same values except which one's negative?
Cosine.
The cosine, so it'll be negative root 3 plus I. And the third one I think is probably our more predictable solution. When we're at 3 pi over 2, we're down here. So that's when our real part is 0, our imaginary part is negative 1. So this would be 0 minus 2i. And that's why I feel like this one is probably the most predictable one out of the three. Like if I cube this, do you see how it's going to equal 8i? Negative 2 cubed is negative 2. Negative I cubed is negative I, which gives you positive 8i. That one's more predictable. Looking at this, I wouldn't have, if I just looked at this, I wouldn't predict that this cubed equals 8i. It does, but it's not as clear as the third one. All right. And if we graphed the three solutions, it would look something like this, making nice and evenly spaced out. What was that?
It's a pinwheel.
It's a pinwheel?
Yeah. Like the pinwheel spins people down the
Oh, okay. Gotcha. No, it's not. All right. So that's our first real attempt at going into the roots in polar. Like I said, it's really just Demoise with just an extra step at the end. So as long as you just remember that. So let's attack number 3. Find the complex cube roots of -1 plus I root 3. First task would be to convert this to polar. When the sides of the triangle are 1 and root 3, what's the radius going to be?
2.
2. So it'll be 2 cis. Alright. My sine is going to be root 3 over 2. My cosine's 1/2. We just did that. We know it's pi over 3. And we're in quadrant 2. So what's my argument?
2 pi over 3.
2 pi over 3. There you go. Alright. Now, one of the differences between number 2 and 3 is that in number 3, they're not asking for any form. So don't be a hero. Our answers are going to be in polar. Whatever this comes out to, do we have any reason to put them in Cartesian form? No. Unless, it's a Friday night and, you don't have anything else better to do, feel free to go ahead and do that. But, pay attention to those little keywords in the question and, you'll determine how much work you really need to do. All right. So take the cube root of both sides. Sean, what would my argument be?
What was that? I kind of just blanked out because
What would my argument be when I take this to the 1/3?
2 pi
Over.
over. Wait, I'm so confused right now.
So when we have it, we're raising it to the 1/3 power. We raise the radius to the power, and how do we combine these two?
You multiply it.
Multiply.
Oh, over 9.
9. Good, yeah. There you go. So my first answer would be the cube root of 2 cis 2 pi over 9. Now I'm really thankful that we don't have to have this in Cartesian form. Over 9's not so nice. All right. All right. Now, we get a proper amount of answers up there, and we do the spacing and it's the same as before, because we've got the cube roots, so they're 2 pi over 3 apart. Tim, what would you get for your first answer? Or your second?
8 pi over 9.
And then how about your third answer?
14 times.
There you go. All right, so there's your solution set right there. Not nice numbers. Glad we don't have to do anything else.
Are we?
All right, so now you've seen those two cube root questions. I want you to take a second, well, more than a second, work with your group, see if you can find the complex cube roots on number 4.